In this video and in this entire lesson, we are going to be focusing on a very important concept, that is gas optimization. So, gas optimized NFTs, that is a particular contract, ERC 721 is an example that I'm going to run you through in this lesson to show you how there's been optimization done in this contract. However, in the introduction, we'll be talking about what are the different ways in which you can optimize gas in Solidity, right? What are the ways in which you can write the contract to optimize gas and Solidity? So it'll be largely focusing on the concept of gas optimization and then run you through an example to show you how it's done, right? So let's get started. The first thing, right? Why gas optimization? This is one of the popular examples in 2022 that stands out. That is towards the end of April, when BAYC, that is your Board Ape Yacht Club, a popular NFT project, released their land sale called Other Side, announced that Other Side will be, land that will be sold in Metaverse. And this particular NFT was, of course, super awaited because BAYC itself is a very popular brand. But the day this particular NFTs were released, there was almost $100 million that was spent just on gas, right? And this is an analyst who posted that you can see the fees in just the last 3 hours, which was close to $100 million, right? You can see 34,365.57 ETH at that point in time was very expensive, just because the contract had nearly zero gas optimizations, right? Of course, this analyst goes ahead to talk about several optimizations that this particular contract could have had, and that's exactly what we will be talking about. This is just one example, but there have been several incidents when there is a huge project that is being released, and when people are trying to buy that project or involve in that project simultaneously, the gas price of the Ethereum network shot up like crazy, right? So, can we as developers make optimizations in the contract in such a way that it doesn't consume so much gas? So let's look at a couple of ways to optimize gas, right? I'm not going to sort of go through this on the slides, because I believe this is one of the best blogs that I came across, which talks about Solidity gas optimizations. It's called Solidity gas optimizations cheat sheet by 0x macro. This has about 12 different types of optimizations that you could do. And we will go through all of them because it's very, very important to understand this as an advanced Solidity developer as to how you can build contracts that are optimized for gas, right? The first thing about Solidity is that you can pack the storage variables. So, for example, when you are sort of layering, you are having different types of storage variables. You can layer them in a way that they get, closer storage slots rather than storage slots that are spread over like this, which will make sure that it will reduce the gas cost, right? So because it will shift the storage slots, which will cost you. So gas is all about accessing, things, computing, right, on the using the network power. So how can you make computation easy, especially when you want to access these state variables, right? So if you have like a before declaration like this, where you're declaring a UN32x, then 256, which is y, and then UN32 again as z, then you can optimize it. You can optimize this for gas and storage slots in such a way that you bring the known data types together, that is UN32 on top, and then UN256. Also, because these are 32 32, they will get the same storage slot, right? So that's why it will be easier to access both x and z together. So this is one of the simple yet powerful optimizations, packing of storage variables. Let's see the next one, which is local variable assignment. So here you can see that in this particular loop, you have the length as being assigned outside, which is going to actually do an S load here, and then it and then it's going to access the length again over here, and then it is going to work with this. So instead of frequently basically instead you can catch the frequently used storage variables in memory or stack, converting multiple S load operations, right? This is the stack operation into one S load. So here, the optimization is that you declare the length outside, right? And then you bring the length into a local variable L, right? So every time you are bringing the, you are going into the function, you can use, you instead of going out, basically instead of accessing the variable from outside, you have declared this variable inside again, and now within this function, you have access to this variable within the for loop. So you don't have to do multiple S loads in this case. So notice that the length variable is defined outside the function loop, right? And therefore, whenever you have to access this, every time you go through the loop, you're going to go outside and have to access that, right? It's a global variable. So instead, you can create this locally and then be able to access this locally as well. These are simple optimizations. Use fixed size byte arrays rather than string or byte array. For example, you can have byte, that is, you can have bytes from 8, 16, 32, like that, right? Byte 1, 2, 3, 4. So if you have a string that you're dealing with, and if it can be limited to max of 32 characters, you can use bytes of 32, which is a fixed length bytes array, instead of dynamic bytes array or string, right? Dynamic variables are always going to require more memory, right? And accessing them is also going to be slower because they are generally in the heap, right? So instead of using dynamic variables, if you can just use static like this, so instead of using string, which is again a dynamic variable, you can just use bytes 32, right? If this can just be limited to max of 32 characters. So this is a quick sort of optimization that you can do whenever you're using strings that could be limited to 32 characters. Now use immutable and constant, right? Wherever you can. And this is one of the basic optimizations that you might have come across even earlier, that if you want to assign a permanent value at construction, use immutable. Because once you use the keyword immutable, then the contract already knows that this value is going to be permanent and it can use the same value across, right? So you can save a lot of S load. And similarly constant, right? So you know that this variable is going to be a constant and it's going to have the same value declared throughout the throughout the contract. So you don't have to worry about creating multiple S loads for that particular variable. Now, using unchecked for arithmetic, where you're sure it won't over or underflow. So 8.0 above, you can save gas cost for checks because that is already there. So if you want to make sure that you still want to, check, make sure to have the overflow or underflow check, then you can have that, you can leave that as unchecked, right? For example, in this example that they have given here below, the variable I cannot overflow because of the condition I less than length, where length is defined as u in 256. So, incrementing I inside unchecked block is safe and consumes lesser gas because by default, this I will undergo this check, right? Which is additional checks, like I said, 0.8.0 has additional checks on for arithmetic overflow and underflow. So, if you say unchecked, then it is automatically going to save some gas for you because you are going to say, okay, no need to perform this compute operation, leave it as is, right? um we are coming to the halfway mark, which is the sixth optimization. Use call data instead of memory for function parameters. Again, this is a very basic optimization. I'm sure you're already familiar with this, that whenever you use call data, it is generally cheaper to load variables directly from call data rather than copying them to memory, right? So only if your variable needs to be modified, then you can use the memory uh, specifier. However, you can otherwise use call data in order to save gas, right? So this is a very simple yet a very powerful optimization. We have 6 more optimizations to go, some of them simple and some of them slightly more complex in nature. But we will take a look at these optimizations in the next video.